Hello, in this video we will be seeing how to find the total number of unique paths in a m by n matrix from the start, that is the top left, to reach the bottom right finish tile, and in the end what we are going to return is the total number of paths that we found from this position to this position. And we will be building a solution in JavaScript and also compute the time complexity and space complexity of the solution that we will be building here. And we will apply the concept of dynamic programming to this problem. Before jumping into the solution aspect of it, let's first try to get a quick understanding of the overall problem statement. The problem statement says that you have a robot in a m by n matrix. Let's say m is 3 here, so you have like 1, 2, 3 rows, and you have n here, which is 7. So 1, 2, 3 up to 7 columns. The robot will start at the top left corner, and the aim here is to reach this tile, which is at the bottom right. And there will be a couple of ways to reach to this position with some constraints applied. And the constraints say that the robot can either move only in the right direction, so I can just keep on going in the right direction here, or the robot can keep on going in the down direction. These are the only two ways the robot can move. The robot cannot go back or move left. It can only go down and right, so it cannot go to the left nor it can go to the top. What I can say is, one simple example is I will go here, keep going to the right, and then once I hit a dead block here in my right direction, I can also go in the down direction. So I can just go down here and I reach my finish. So this is one way to reach it. Another way can be I can just keep going down. I hit a roadblock here, then I can keep going right, and this is another way to reach the solution. So I just found two ways to reach my solution. Now, like this, I have to find all the paths which I can take to reach my finish tile in this matrix. That's the whole problem statement. And what we can do is, let's first just try to see how we can solve the problem. The concept which I mentioned here that we'll be applying is dynamic programming, and dynamic programming states that we will break the problem into smaller sub-problems and then club all the solutions of the sub-problems to get our final solution. And the tricky part of using dynamic programming is to find which is our smallest sub-problem that we would like to solve. And while we analyze this problem, I will try to find the smallest sub-problem that we want to solve, and then aggregate the smaller sub-problem solutions to reach our finish, which is this tile here. Now, we said that we can go in the right direction. So what that means is, from here I can go here. To reach from here to here, there is one path. So I will say this is 1. To reach from here to here, there is also one path. From here to here, there is one path. From here to here, there is one path. From here to here, there is one path. And from here to here, there is one path. Because we can keep going in the right direction. Similarly, we can also go in the bottom direction. So let's say from here to here, what I'm trying to do is, find the smallest sub-problem that I can solve. So I'm just taking like these two blocks and I'm saying from here to here, how can I go? How many ways I can go? And it is just one way I can reach here. Similarly, I just consider then these two blocks from here to here, how I can go? There is one path to reach this position. Similarly, from here to here, I have one path to reach this position. When I consider this, I just consider these two blocks and say, okay, from this block to this block, how I can reach, how many number of paths there are. And this gives me once in the down direction and once in the right direction. So this is like the smallest chunk that I broke it into to try to solve the sub problem and to reach a solution. Now I broke it into blocks of 2 to try to find my solution. Now what I will do is I will try to go a bit further. So from 2 I will now try to go to blocks of 4. So I will now say that from here, before I just considered 2 blocks, I said, okay, from this and this block, how many ways you can go from here to here. Now I will say how many ways I can go from here to here. So I will now consider 4 blocks. So this. And right now I don't know what this is. And I will try to see if this suits a smallest sub-problem use case to reach the larger solution. Now, please note that we saw that the constraints that we have are that you can either go in the right direction or you can go in the down direction. So I will just ignore the rest of the blocks and I will only focus in these blocks, in this just 4 blocks that I have. And I will say that, hey, how can I reach this position? Either we can come from the top, so we can come from here to this position. Please note that we are only considering this. Let's just focus on this part for now. Ignore the rest of the blocks that we have. So you said you can reach from here, and you said you can go in the right direction. So we will go in the right direction here. So you can either come from here or you can come from here. This gives us 2 ways to reach this solution. Now we saw that we had a smaller subproblem. We said just reach from here to here, here to here as 2 separate parts, and then we just increased it to reach a bit bigger subproblem wherein we said how do we reach here now. So you can go from here to here and here to here. Similarly, what we can do is expand a problem statement now. So now what we will do is we will also consider these blocks, these 2 blocks that we have here. So this block and this block. Now I will say what is the number of paths to reach this position. So I calculated for this position. Now I will say what is the number of paths to. What I'm doing is slowly increasing subproblem scope. So the subproblem was here to here, then it became here, and now it's up to here. I'm just trying to see that I can repeat some pattern of some problems to reach the grand solution that we are looking for. And how can I reach here now? Again, the same constraints apply. You can either go down or you can go right. So if I combine these 2, it is 3. So I can reach here in 3 number of unique paths that we have possible in this scope. Now I am starting to see a pattern here, which is, let's say I was here. So in the first block that we discussed here, let's say this was I, j here. What we did was we got the number of paths in the previous block, which is this one, and we got the number of paths in this block, and then we added them to reach this solution, which basically translates, if I try to make a I comma j equivalent representation of this, will be something like this is I minus 1 and I being the row and j being the column, and this one will be I comma j minus 1. So I added this one and this one, and what we can say is, to reach this I comma j, what we basically did was we found the value at I minus 1 comma j and added it to the value at I comma j minus 1. This is something, let's just keep observing. Now, after we evaluated for this one, let's also evaluate the same thing for the next element, this one. What we did for this one, if this was I comma j, is also we took the top one, which is I minus 1 comma j, and we took this one, which is I comma j minus 1, considering this was I comma j. So I am starting to see a pattern now, that if I keep adding the top and the left outcomes, I will reach my current block solution, that is the number of paths to reach this block. And this is what I was looking for. So I needed to form some kind of sub problem that I am trying to solve, and it looks like this should suffice for us. What I mean by this is, if I want to find the number of paths to a specific block, I just add the top and the left blocks and try to get my solution. Before confirming that this is a sub problem, what we can do is we can try to apply the same thing in a repeated fashion and see if we reach a solution. Please note that the solution we are looking for to reach is here. So I will just repeat this sub problem that I formed throughout now. So I will say, to reach here, this position, I can come from top or I can come from left. 2 plus 1 gives me 3. Same way, to reach this position now, I will say I will come from top and left, giving me 6. So now what we did is basically expand our problem statement, and our sub problem is now covering up to this part. So we keep expanding our sub problem until we reach this point. Now I will also expand my sub problem to this block. So you keep on slowly expanding it. 3 plus 1 is 4. Similarly, 4 plus 6 is 10. So I have expanded my sub problem up to this point now. Up to this point, I will keep expanding it further, and I will expand it up to here. So I will say 1 plus 4 is 5. 5 plus 10 is 15. I have expanded the sub problem up to this point so far. Then I will expand my sub problem further to this point now, to this point, and I will say 1 plus 5 is 6. 6 plus 15 is 21, and similarly I will go all the way now up to here, and I will say from down here 7, and now I will expand it up to my finish, which is I take from top and left, and it gives me 28. I saw that I could expand this sub problem to reach my final solution. I kept on expanding and combining my previous and the top number of paths to reach my current number of path solution, and then I just went on solving this sub problem expanding the scope of the sub problem right from this point up to this point. So we kept on expanding it. That's basically the concept of dynamic programming that we applied here. We broke it down into smaller chunks. First we saw that to go from here to here, the number of paths were 1. So that's why we put it 1 here. And similarly, to go all the way to here, like from here to here, here to here, here to here, it was all 1. Because you can only move in the right direction. And similarly, we gave it 1, 1 here, because you could just keep on going in the right direction here and down direction here. So from here to here, as you go down, it is just 1. To convert it into code, what we did is we maintained this array with ones on the top right and this edge. So this edge and this edge we filled with ones, and then we try to reach a solution. Usually what happens with DP solutions is we pre-fill the initial sub-problems. That becomes a starting point, and then we keep combining and try to apply a relationship between the sub-problems to reach a grand solution. And that's pretty much it in terms of the outcome that we were looking for. Now let us explore the JavaScript solution from the concept that we have covered so far. We said that we will be using a DP approach. So what we will do is, in our DP approach, we need to keep track of the small solutions that we are building. We saw that we pre-filled this the top row with ones, and we pre-filled the top column with ones, and then we stored the smaller solutions here, 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 up till we reached our final solution. So I need some kind of DP tracker to keep track of all our solutions to our small sub-problems to reach the bigger solution. And to do that, what I will do is I will use a DP 2D array in case of this example, and I will say something like this: give me a new array of the number of rows that you have. Just fill it with something. That something really doesn't matter in so far. And then we will say, in this array of number of rows that you have, build another array of n's and then fill it with 1. And this is to pre-fill our top row and top column, this one, because we said that to go from here to here, just one path, from here to here there was one path. So we have pre-filled with our solutions. So the first row we solved and the first column we solved. And you will say now that, hey, you are saying just pre-fill the first row and the first column, but here you're pre-filling everything. This is just for the sake of simplicity, because I don't want to put a condition that just pre-fill the first row or the first column, and then we just proceed ahead. Now what I will do is, in the end, what I am looking for. So I have to return my output in the end, and the output lies here. This translates into my DP array, which I have created a 2D array here as m-1 and n-1. That was the solution that we were looking for, and that basically lies here. So this is m-1 and n-1 in the matrix that we have, and the DP array is going to store all the outcomes up till the final outcome we are looking for, and then we just return the final outcome from the sub problems that we had. I will, as we said, we need to keep expanding the scope of the sub problem. So you start small and then you keep going towards the end, which will represent into code something like this. So I goes up to m, I plus plus, and j goes up till n, j plus plus, and logic for subproblem goes here. Now you can see that I have said to initialize I from 1 and j also from 1 because we have already pre-filled the first two, that is the top row and the top column, we have pre-filled with ones based on the logic that we said. That we decided that we will find these paths manually for the top column and for the top rows, because the condition that we had that you can only go right or you can only go down. And this will keep expanding the scope of our subproblem, and then the expression that we had written earlier, which is this one, which basically translates to find the solution to this point, you go on the top and you go on the left and you combine them, and the output will go in my DP array that we have. So DP of I j will be DP of something plus DP of something. And let's take the top one, which is represented basically by I minus 1 and j, and the left one, which is represented by I comma j minus 1, which is this one. And as we saw here, we just added this one and this one, and the outcome goes in my DP array against the specific tile that we were looking for, which was, let's say, I comma j. In this example, you added this one and this one, and that's pretty much the solution that we wanted to build. So you will keep expanding the scope of this subproblem. So the key element that we were looking for is this, that is a smallest possible subproblem and how we solve our smallest possible subproblem, and then we just extrapolated it to reach our final solution. And we used a DP array to store all our subproblem solutions as we kept building, and then we kept using the outputs of these subproblems as inputs to our next subproblem. That's the whole gist of the implementation. And in terms of time complexity, what we will say is it will be big O of m into n, because the time it takes will depend on the number of columns you have and the number of rows you have, as you saw here, and then you keep on going in this loop until that time. And the space complexity will also be m into n, because you said you use a DP array and we pre-fill it with this once. So as many number of rows and columns, that much space we need in our 2D array, and then we just return the final output that we have here. And that's pretty much the solution. I hope you liked the video. Please like and subscribe. Thank you.